Welcome back. My name is Steve Miller. I'm a math professor at Williams College, and I'm with my son, and we are going to do another lecture on math. This is part 2 of the From Pythagoras to Pi. And so let me begin the slideshow. Okay. So we ended the last time by looking at Pythagorean triples. So these are numbers a, b, and c, such that a squared plus b squared equals c squared. We found that there was a general formula for them. So if you give me any two integers p and q, then we can take a to be 2pq, b to be p squared minus q squared, and c to be p squared plus q squared. How did what work again?
The PQ.
So that was the algebra we did last time, and we looked at, here was the line y equals mx plus b hitting the circle of radius 1, and we have the line going through the point 0, negative 1. Okay. So we saw that the equation was y equals mx minus 1. So we said, well, when do these two equal? So we said y equals mx minus 1. We substituted, we did some algebra, we solved for y, we cleared denominators, and then we said since m is a rational number, a ratio of two integers, we could write m as p over q, and we got all the triples this way. And so we noticed some of our fun triples. You know, there's the old 3, 4, 5.
I think it's probably the 12, 5, 13.
There's the 12, 5, 13. There's the 24, 7, 25. There's the 60, 11, 61. And what do those all have in common?
One prime. At least one prime.
They all have at least one prime. What else do they all have then?
They're all like original.
Well, they all can't be reduced. So you know, the 6, 8, 10 is really just the 3, 4, 5, just rescaled. But there's also something interesting in the 5, 12, 13.
They're not next to each other?
Well, what do you mean by not next to each other? The 7,
there's like one that's like really low, and like two of them are right next to each other.
Yeah, two of them are adjacent. So as a nice question, are there infinitely many triples where one number is one more than another?
Yes.
So it looks like yes. So the question is, so could p squared plus q squared be one more than p squared minus q squared?
What?
Could p squared plus q squared be one more than p squared minus q squared?
No.
No. How much do they differ by?
Q squared. 2q squared.
2q squared. And 2q squared has to be at least
bigger than that.
What's the smallest 2q squared could be?
0.
Right, but we're not going to take q equals 0.
Then 2q squared.
Yeah, what's the smallest that could be?
2.
2. So
well, technically it could be smaller.
Well, but we would take q to be integers, right?
Yeah.
So we know that if there are two that are adjacent, it can't be the last two columns. It has to be 2pq has to be 1 less than p squared plus q squared. So when would 2pq plus 1 equal p squared plus q squared?
When would what?
So when would 2pq plus 1 equal p squared plus q squared?
Oh, like
so we'll,
4, 3, 5. For
so
all
that
the
one
original
works.
triangles, ones that can't be reduced.
Right, but will that happen infinitely often?
Yes.
So that will be an exercise to think about. Now, the infinitely many p and q such that 2p plus 1 is p squared plus q squared. We'll let that to think about. So here's some trig identities that we're going to need to get a formula for pi. So the first is 1 equals cosine squared a plus sine squared a. So where have we seen that before?
That's Pythagoras.
Yeah, that's the Pythagoras theorem. So we have a right triangle, and we have a hypotenuse of 1 and an angle of a. Then the side adjacent to the angle of a is cosine a, and the side opposite is sine of a.
And then you could switch that.
And
switch
right,
angles.
right. So if we put a b up over here, then the sine of a would actually be the same as cosine of b. The other is the more involved one. Cosine of a plus b is cosine a cosine b minus sine a sine b. Sine a plus b is sine a cosine b plus cosine b sine a. So we're going to show how to prove these. So we just need the special case for what we're going to do when a equals b equals x halves, but we will prove it in general. Now, if a equals b equals x halves, what does a plus b equal?
X.
X. So when we have cosine of a plus b and a plus b are both x halves, cosine of a plus b is cosine of x. What does the rest of the stuff in red become?
X.
Well, what are we taking for a? A equals
1/2 x.
Or x
0
halves.
Then.
A equals x halves.
It would equal 0. Right?
What would equal 0?
What's that? What's the rest?
Well, let's substitute in. What do you get when you put in a equals x halves? This becomes
cosine ax half.
just
Cosine x half.
cosine
sorry.
x half, and the next piece becomes
Cosine x half.
minus,
Cosine x half.
nope, minus what?
Sin
Minus sine
x half.
times,
Sine x half.
so it's not 0.
It's not, yeah.
And what does this become? The sine of x halves
Same
plus
thing
x
as
halves.
that, just flipped.
So now this becomes
Oh, wait,
sine,
no, that's added too.
sine x halves, cosine x halves, plus cosine x halves,
Plus
sine x halves.
Wait, is the cosine b times sin a, or is that supposed
Well,
to be?
well, right now I'm not assuming a and b
Okay.
add up to 90, so you don't have
No,
any
okay.
simplification.
Right.
So I'm just using this formula in the special
Yeah.
case when a equals b equals x halves.
Hmm.
Now, how could we simplify cosine of x halves times cosine of x halves?
Just put x. Like, just put cosine x.
No, because remember the x halves is the argument.
Wait, is it cosine x halves times?
It's cosine x halves
That's why I
times
had
cosine.
asked
Yep.
that earlier.
Yep.
You said no.
Okay.
Okay, then yeah, that would just be cosine x halves squared.
Good. And it would be minus sine x halves squared.
Yeah.
So we can simplify it like this. And the other one, since they're the same, is just 2 sine x halves cosine x halves. Now we have cosine x halves squared minus sine x halves squared. So if we go back to our first trig identity, 1 equals cosine a squared plus sine a squared, this is true for any angle A. Look how we have a cosine x halves squared minus a sine x halves squared. Does that suggest what it might be a good choice for A?
X halves?
Yeah, then we would get, if we take A equals x halves, the first equation here gives us cosine of x equals cosine x halves squared minus sine x halves squared. And the second one, 1 is equal to cosine x halves squared plus sine x halves squared. So what should we do to these two equations?
Add them together.
And what happens when we add
You
them?
get cosine x plus 1
On the left side,
equals
good, equals.
2 cosine x halves squared.
Right, and the signs are going to just cancel. So we get cosine x plus 1 is 2 cosine x halves squared. Now what should we do?
Get rid of this. Divide by 2.
Divide by 2. And so we get cosine x halves squared is cosine x plus 1 over 2. Now what do we do?
Take the square root.
Now we take the square root, and we'll get cosine of x halves equals the square root of cosine x plus 1 over 2. Now you do similar work. We know that sine of x is 2 sine of x halves cosine of x halves. We just showed how to relate cosine of x halves to cosine of x. So we can solve for the sine of x halves as sine of x divided by 2 cosine x halves. We know what the cosine of x halves is, and we now get the following formula in red. And what's great about these formulas is they express cosine and sine of x halves in terms of cosine and sine of x. So when we have the angle, this tells us what the answer is in terms of the bigger angle. So if we know 45 degrees, we then know 22.5. If we know 90 degrees, we then know 45. So here is our big trig identities. We need to prove this formula. We just did the special case when a equals b equals x halves. Now let's prove it in general. So when we look over here, here is the angle A, here's the angle B, and this whole thing is the angle A plus B. So can you show me on this where cosine of A would be? Yeah, use your finger. So cosine A would be...
Is it that? Like that? Well, is it the red line?
Well,
oh wait, no,
no,
cosine.
the red line and the blue line have the same length as what other line?
The red each other as that one.
Yes, the black line. All of these have length 1 because it's a circle of radius 1. So so where would be the cosine of A?
The black line.
Well, the black, and that's 1. And that's saying that no matter what A is, the cosine would always be 1. So how do we form
that?
So let's go back to how we define things. So we have, if we have a hypotenuse of 1 and an angle of A, we need to make the triangle.
Yeah.
And so you have to make a right triangle, and then the bottom is cosine of A. That's okay. The bottom is cosine of A, and the height. So now if we go back over here, how would we get cosine of A?
If we draw a line down.
Yeah, if we draw a line coming down over here, then cosine of A would be all the way down to here.
Yeah.
And sine of A would be up to here.
And then if for B, we would just do the same thing.
Yeah, we could
just like up there.
we could draw a right angle from here down to the
So
How would we get cosine of a plus b? Where would we draw the line now?
a plus b
Yeah, cosine of a plus b.
from there.
Here we draw the line from the top going all the way down. I really hope the mouse is recording all this. And so here's just putting in some of the lines. So here is the line, and this gives us cosine of a down here and sine of a up here. Over here, if this whole thing is 1, and this is angle B, then the hypotenuse up to here is cosine of B, and up to here is the sine of B.
Yeah.
And then as was remarked, if we draw this green line all the way down, this bit down here on the bottom would be the cosine of A plus B. So here's the cosine of A plus B. We want to express the cosine of A plus B in terms of cosines and sines of A and B. So we need more right triangles. Any thoughts as to how we could get more right triangles?
We could try.
Yeah, we could draw a line from here parallel to the x-axis.
Yeah.
And what else could we do?
We could draw it down. Wait.
Yeah, parallel to the y-axis. And so if we draw those two lines over here, from here to here, this is the cosine of A plus B. From here all the way to this green line, that's the cosine of A times the cosine of B. And the reason is if this angle is B and this is 1 all the way up here, then this is sine of B here, and this is cosine of B up to here. Now it's like we have a right triangle, but the hypotenuse is cosine of B. Its angle is still A, so it's the hypotenuse times the cosine of A, and that's why this thing over here is the cosine of B times the cosine of A. But we can write them in the order. So we want the cosine of A plus B. We have cosine A times cosine B. Is that too much or
Too much.
too much? So we have to subtract off a little bit. What do we have to subtract off?
That.
Yeah, we have to subtract off this little bit over here. But this little bit over here is the same as this little bit in this triangle up over here. So we just have to figure out what that is. So to figure this out, we know the hypotenuse is the sine of B, so we just need that angle over there. Well, if we blow up this little part, if this angle is A and this is 90 degrees, let's call this angle C. What does A plus C have to add up to?
A plus B.
A plus C.
What, 90?
90, because the angles in a triangle is 180. Yeah. We have 90 over here. So if this is C, do we agree that the angle on the opposite it through here is also C?
Yeah.
Another way to say that if this is C, this is 180 minus C over here,
yeah,
because it's a straight line. And if this is
yeah,
180 minus C, then that's C. So we're proving a lot of geometry facts. It's often fun to just chase through the angles. So this is how the mouse keeps vanishing. This is C, 180 minus C, this is C. Well, this is a 90-degree angle here, and we know that A plus C equals 90, so this has to be A over here.
yeah.
And since this is a right angle here, what does this have to be?
A right triangle.
Well, right, it's a right triangle. So
C,
if this is A, that has
C.
to be C. So now we know that this over here is also angle C. So what is the angle all the way up here?
A.
A. And so now we know here we have a right triangle. The hypotenuse is sine of B. This is the angle A. So this length here, it's the hypotenuse times.
Cosine B.
No. The angle is A.
Yeah.
So it's the hypotenuse times, is the opposite, is that the sine or the cosine?
Sine.
Sine.
I would say cosine B.
Right. So
it
it would be the sine of B, the hypotenuse, times the sine of A.
Yeah.
And so that's how much extra stuff we have. So from here to here was cosine A times cosine B. From here to here was sine A sine B. So if we subtract, we get cosine A plus B. And that proves the first formula, and a similar analysis gives the second. All right, so now we can finish off the lecture with our formula for pi. So this is what we were building up to. And we will express pi using just one number.
Pi?
No. Although that is another way to do it. So we're going to look at circumscribed and inscribed circles. You could also do things with areas. We're going to do things with perimeters. So what is the perimeter of a circle of radius 1?
I actually don't know. For 1?
No. So what's the formula for the area of a circle?
Is it pi r squared?
It's pi r squared. And what's the area for the perimeter?
Perimeter, is it just r squared?
Well, no. Well, first of all, what units has to be?
I don't know. I forget what a
Well,
circle
perimeter, is that a length? Is it an area? Is it a volume? So do you think it should be the radius squared? What power should the radius occur? Area has a radius
360.
squared.
Oh wait, no, the perimeter is 360, right? No,
No, that's the number of angles.
Yeah.
But what should be the units of perimeter?
What do you mean?
Well, the units of area would be like meters squared, and that's why we have a
Oh.
radius squared. What should the units of perimeter be? It is a,
Right.
it's a length.
Yeah.
So if we're measuring the area in meters squared, what should the perimeter be measured in?
Meters.
Mm.
Meters. Just meters.
Just meters. And so if the area is like r squared, what should the perimeter be? What power of r?
Just r.
R. And so the perimeter of a circle is 2 pi r.
Oh yeah.
And so if the circle has radius 1, what would the perimeter be?
2 pi.
It'd be 2
2
pi
pi.
r, which is just 2 pi. So as we take more and more sides of our figure, it's going to be a better and better approximation.
Yeah.
Now, the ancient Greeks liked to just use the straightedge and the compass. So they couldn't measure lengths, but they could draw straight lines. And it's easy to do squares and equilateral triangles and then subdividing those. So we're going to do it with squares. So here's an inscribed square. It's inside the circle. Here's a circumscribed. And if we now go to an octagon, what we do is we basically take each of these angles and cut it in half, and we replace each side with 2 more sides of equal but smaller length. And you can see that for the inscribed, it looks like the perimeter has definitely gone up, and the circumscribed, it's gone down. They both still have, for instance, this side over here, but now rather than these 2 bases, it just has the smaller hypotenuse.
Yeah.
And even though the hypotenuse is longer than either one of them, it's not longer than the sum of both.
It did go down, right?
So it does go down. And so we'll look with the inscribed figure. You could, of course, do the
'Cause
circumscribed.
It still goes down with that, right? Or,
Well,
no,
do you-
for the inside it gets bigger.
yeah, for the inside, it gets bigger. For the circumscribed, it gets smaller. So for the inside, if we have a square, if we have the radius is of length 1, we have a 45, 90 triangle. Here's our right angle, and here's 245 degrees. So by Pythagoras, 1 squared plus 1 squared is the hypotenuse squared. So the hypotenuse squared is 2, so the hypotenuse is square root of 2. So what would be the perimeter of the square?
Well, the square root of 4 square roots of 2.
Yeah, because we have each side is root 2 and we have 4 of them. So the perimeter is 4 square root of 2, which is about 5.656. 2 pi is about 6.283. It's not great, it's not terrible. If we divide the square, however, and make an octagon, it gets better. So what we would want to do is we would want to, here is the square. How do we do things? Well, if we make a 45, 90 triangle like this, the hypotenuse is 1. This is going to be the sine of 45, which is 90 over 2. This is going to be the cosine of 45, which is the cosine of 90 over 2. And we know that if this is 1, then this side squared plus this side squared equals 1. They both are the same value, and we get that they are both going to be root 2 over 2, because it's an isosceles triangle, so these 2 sides are the same. And if you square root 2 over 2, you get 1/2. So we can use our angle formulas to find 45 in terms of 90. And for the octagon, if we used 45 degrees for the square, what angle would we have to use for the octagon?
Wait, what?
So the square, we used 45 degrees.
Yeah.
And for the octagon, if we want to double the number of sides, what would we do to the angle?
Double?
Not double. So when we go to the octagon, do you think the angle is getting bigger or smaller?
Yeah, smaller.
So instead of having 45, instead of doubling it, what should we do? Divide by 2. And so we'll have 45 over 2. And so if we look for the octagon,
so on and so forth.
Exactly. And now,
that would be 45 divided by 2 divided by 2.
Which is 45 divided by
4.
And then 45 divided by
8, I think comes next.
Yeah,
16,
and
32,
16. That's right.
64, 132.
That's right.
Whatever comes after that.
Wait, 64.
I think I said something wrong.
It's not 132. It's 128.
That's what I said.
Yeah.
Yeah.
And so when we look at this,
You know it.
we know that the octagon has 8 sides, and these come from halving the angles of the square. For the square, half a side was the sine of 45. Now for an octagon, half of it's going to be the sine of 45 over 2. And so we use our formula. We first calculate the cosine of x over 2, and we then calculate the sine of x over 2. And so we have our formulas. And so we can get, if x equals 45, then the cosine and sine of 45 over 2, we can get in terms of the cosine and sine of 45. And so the cosine of 45 and the sine of 45 is root 2 over 2. So we get the cosine of 45 over 2 is the square root of 1/2, 1 plus 1 of root 2. The sine of 45 over 2 is 1 divided by 2 square roots of 1 plus root 1 over root 2.
Yeah.
And we have 8 sides. And so if we multiply the sine of 45 over 2 by 8, we get 4 over 1 plus 1 over root 2, which is about 3.06147, which isn't that bad. And so here is a couple of values. So what we're doing here is we're calculating.
You just count pi as 3.14, like you're golden on the last one.
So with 64 sides, we're already getting the 2 digits. So I'm
We're actually
calculating.
getting 3 digits.
We're actually getting 3 digits because we do have the leading digit. So I'm calculating not the perimeter, but the semi-perimeter. What do you think the semi-perimeter is?
Smaller than the perimeter.
Well, what do you think? What do you think semi means?
like just like one side.
Well, but it's a circle.
Huh.
So for a circle, what do you think? Or for a square, the semi-perimeter would be how many sides of the square?
1,
Not 1.
2,
Well, think. Where have you heard the word semi in?
semicolon.
Semicolon, which is like half a colon.
Half a circle.
Semi-final. So 2. So if you had an octagon.
It's funny, you go to like the boring things. I play sports. I go to like the geometric.
That's
thing.
right.
And then that. Okay.
So, semifinals, half. So over here, it's half the perimeter. So notice that the first one is 4 minus 2 root 2. The second is 8 over blah, 16 over blah, blah, and then 32 over blah, blah, blah.
So what? Use a different tone.
So what patterns do you notice?
It just like adds another 2 to each thing. Like you take what was there before, bring it down. Now the last one, you add another 2 plus 2 to it, and then take that whole thing down. And
be more specific. So
like you take those 2 down.
Okay, so we take these 2 factors in the denominator down, then we add a new factor in the denominator.
And you add a square root sign
plus
2.
Good. So
then take that down.
Good. So what we do is we take the largest factor from the previous, put that inside a square root, and then add 2 in front of that. So we start off with 2 plus root 2, then 2 plus square root of 2 plus root 2, and 2 plus square root of 2 plus square root of 2 plus square root of 2. What about the numerators?
They're powers of 2. One less than the actual.
So it's 8, 16, 32. What would you predict the next one would be?
64.
Now, the program I was using...
And as you just taught me, 128.
Yep. The program I was using before simplified, and it has 4 minus 2 root 2. Does that look different than everything else?
Yes.
So let's see if it's different or not. So we started with...
It looks different, but it's probably not.
It's probably not. So what can we multiply any number by without changing it?
1.
1. So you can always multiply by 1. The difficulty in math is figuring out how should we multiply something by 1. We want to get 4 over 2 plus root 2. That's what we think it should be from looking at this. We think it should be 4 over 2 plus root 2. But we have 4 minus 2 over squared 4 minus 2 root 2. What should we multiply? We want to multiply by 1. So if I want to multiply by 1, can you give me another way of writing the number 1?
3 over 3.
3 over 3. Excellent. How else could you write 1?
4 over 4.
4 over 4. But given that we want 4 divided by 2 plus root 2, what do you think we should choose for our denominator?
2 over 2.
2 plus root 2. And so we should take 2 plus root 2 for the denominator. We should take 2 plus root 2 for the denominator. What should we take for the numerator?
What was it?
So you just said we should take 2 plus root 2 for the denominator. What should we take for the numerator?
4.
No. We want to multiply by 1.
4 over 4.
So if we take the denominator to be 2 plus root 2, and we want our number to be 1, what must the numerator be?
2 plus root 2.
2 plus root 2. So we take 1 as 2 plus root 2 over 2 plus root 2, and we multiply the 4 minus 2 root 2 over 1 by 2 plus root 2 over 2 plus root 2. So if you multiply two fractions, you multiply the two tops, and you multiply the two bottoms.
It does even.
So do you remember, how do you multiply two expressions like this? You use
so the outside to the inside.
So
and
first,
outside to
outside, inside,
to
last.
Inside to outside.
So what's the first? The first is going to be
4 times
4 times 2. Then the outside.
The 4 times.
Nope. Outside is going to be minus 2 root 2 times.
Oh, I was going to.
Yeah, there's lots of different ways of doing it.
Yeah.
So this is multiplying them all out. 4 times 2.
We can simplify that to just
So
4.
4 times 2 is?
8.
What's 2 root 2 times root 2?
Oh, that's negative.
Yeah, negative. So what's 2 root 2 times root 2?
2. Right?
You're saying 2 root 2 times root 2? So what's 2 root 2 times root 2?
2. Well, if it was just root 2 times root 2, it'd be 2.
Good. And so if we have 2 times root 2 times root 2,
2 is 4.
it's 4. So we have 8 minus 4, which is
4.
4. And then we have a minus 2 root 2 times 2 plus a 4 times root 2. How many root 2's is this?
4.
So we have minus 4 root 2 plus 4 root 2. And so it does simplify the 4 over 2 root 2 as we had hoped. It was just another way of writing it. And as you predicted,
I'm a genius.
the next one would be 64.
Now that looks annoying.
But notice now, instead of having 3.14033, we have 3.14128.
Well, it really goes 3.14159.
So it's not terrible.
So we go off by like the 3.
But we are making now a figure that has 128 sides, which is a pretty large figure.
I don't know if I can count that high. We should see.
But we are getting an approximation for pi that only uses the number 2, which is not bad. So this concludes our second lecture from Pythagoras to Pi. I hope you enjoyed this. Good night.